In this presentation, I'm going to make a brief introduction to the HEC-SSP program. HEC is a hydrologic engineering center of the U.S. Army Corps of Engineers, and SSP is a statistical software package. This is the user manual of that program. And in this case, where we are interested in to describe this component, that is fitting extreme event probability distribution to this historical data that could be, for example, maximum annual flow recorded in a given river, in a given gauging station. To download the program, this is the web page of the U.S. Army Corps of Engineers, and then you can look for HEC-SSP, download, and then here you can download the latest version. The same in the case of documentation. In the documentation, you also can download the latest version of the user manual. Well, in this software, you can using the software you can perform this type of analysis. There are different type of analysis. All of them are described in the user manual of the software. And, but we are interested in this one, the distribution fitting analysis. In this case, this component provides a tool to fit up to 19 different analytical probability distribution and using two fitting methods. The first one is the standard moments that we described in the previous presentation, but also we use another method that is L moments. And in addition to that, to evaluate the goodness of fit, they use two methodologies, that is the chi-square, but also the Kolmogorov-Smirnov test. This distribution can be fitted to a series of annual maximum values of flow or water levels or depth of precipitation associated with different rainfall duration. In our case, we are going to, as an example, we are going to use this data that is in this Excel file that correspond to the Paraguay River. Paraguay River is in the station Puerto Mortiño, and the data is from 1964 to 2019, and we have is a series of maximum annual flow in this station, Puerto Mortiño station on the Paraguay River. And the format is this, that we need to specify two columns of information. The first column is the date and time, and the format that is used is this one. First, you have to write the date, then after the day, the month, and then the year. And in the inflow column, and then you have to introduce the value of the maximum flow, in this case, maximum flow that occurred in that year. Well, in this case, we have like 56 years of data. Okay, and then the first step is to import this data into the software. To do that, let's go to the program. Going to open the program, and then when you start with a new story, in this window is going to appear where you have to introduce the story name and description and the file and the unit system. That is very important to define the unit system. In this case, I selected international or metric system. Okay, the next step after you introduce the basic information for the story properties is to import the data. And then you go to data, new, and, uh, uh, and then appear this data importer window. And then there is different ways to introduce the data, the information. And in our case, we are going to use Microsoft Excel. And what you have to do is look for the file that in our case is this one. And when you do that, this appears this window, and then you have to select all the information, uh, date and the inflows, and click here in import. And then here you have all the information, all the data, and then you can introduce the data units. In this case, it's going to be cubic meter per second, and also you can tabulate the data, or you can plot the data. Also, here we have all the data, and when you finish, and then you have to click in this tab that is import to story DSS file. But I'm not going to do that because I already did it, and that information is stored right here in this um, in this file that we have here. Okay, then that's the first step. The second step, and then is going to analysis, a new analysis, and then select the type of analysis that we want to do. And in our case, is distribution fitting analysis. Okay, and then here you have to introduce the name. For example, in our case, this is Paraguay River. Um, describe the Paraguay River. You can describe the. I don't know what's happening here. Okay, the Paraguay River. You can describe the story. But what is most important is the data set. We have here the data set, but when you open this menu, it appears in here, and then you select that, and then immediately um, you upload all the information and have this kind of figure. In this case, this is a cumulative distribution function associated with this historical data. Okay, I'm going to cancel this because I already did this. I'm going, yes, I'm going to cancel this, and then because I have that information right here. Um, Now, when you have this the data, you also can click on that data summary statistics. When you have the original and processed data, I am going to explain this later. Here, for example, you have the minimum, the maximum, minimum value, maximum value, the median, the mode, the sample size, 56 years of data, the mean value, the standard deviation, the skew, kurtosis, and so on. And and the reason is because you have the original data, but you also can filter the data. In our case, in our case, we don't need to do that because this is when you have you need to filter data by season or establish a minimum threshold or maximum threshold, but in this case, it is not necessary. Then the filter and the original are going to be equal. An important aspect is this parameter type, because in this case, it's flow, but you also have precipitation or a stage, but in our case it's flow. Now, why this is important? Because when I'm going to go to analysis, in the case of analysis, I have a distribution filter that if we click here, the filter using the parameter, and then the parameter was flow, and then using that parameter, the software, and then select the probability distributions that are recommended for that type of parameter. If you, instead of flow, the parameter is precipitation, the probability distribution are going to be different. And then we can have this graph here with, again, this is the cumulative distribution function, where I have in this case, select the distribution log normal. And in this tag, we have the methodology that we are using to fit that distribution to the historical data. We have two methodology, the standard product moment and L moments. And if I change for L moment or standard product moment, we're going to have different results. And to evaluate this, the goodness of fit, we have two tests, chi-square, but also Kolmogorov-Smirnov. Okay. And okay, plot option. In the case of plot option, let's see this type of plotting. Okay. In the case of plot option, here we define the plotted position parameter. In this case, the default value for parameter B is 0.3. But you can change that value or with selecting another option, or simply introduce a new information here. In that case, in this case, we're going to use the default value. The output frequency ordinate we're going to use as an axis the exceeding probability. And to analyze the goodness of fit, we're going to use number of being 20 intervals. 20 intervals to, for example, to do the chi-square analysis. Okay, and let's continue then. That's the plotting options. Okay, confidence limited. We define here the confidence limits. And the default value are between 5% and 95%, and well, and so on. Okay, now I have this the historical information that to do this graph we are using the plotting position as I described in the previous presentation. Now we can choose between the different distribution. For example, this is the fitting of log normal, and this is log Pearson. This is generalized stream value. Okay, but here there is a summary of the statistic of the two methodology of test, Kolmogorov-Smirnov test and chi-square test. And if you see the generalized stream value and log Pearson 3 and log normal have a similar or equal values for the Kolmogorov, Smirnov, and chi-square. That means that those are the three most most important distribution to fit in this case to fit this data. That using those distribution, we can get a good fit of the historical data. And then this is for the standard product moment, which we can change to the L moments, and then we're going to have another value, but continue being similar to the standard product moment. Okay, now to go to the next step, that is the results, that you have to select and then one distribution. In this case, we're going to select log normal, and then we're going to uncheck the rest of the distribution, and then we have log normal. We can click here and have the confidence interval and the median curve. And if I click here, I also have the expected probability curve. That expected probability curve is similar to the median curve. And then we can go to the result, and the result, we have all this information about the result. Sorry. Before, I have to press this accept selected distribution. And then after I press this accept selected distribution, we can go to the result, and then here we have the result. And okay, you have all this information about the statistics, the parameters, and the chi-square in this case. But this is what is important. But this is expressed as percent chance of exceedance. That means that one is a 100-year storm, and 2 is 50 years, 0.5 is 500 years, 100 years, 0.2 is 500 years, and so on. And then this is the median curve. In this case, the 100-year is this, and the expected probability curve is this, and the confidence interval, those values for 5 and 95%. Well, you can select all this information. You can copy to the clipboard, and then I already did it. Okay, we can paste to the here. But you also have a report, and then you have all the information and the description of the results. And well, with this, we finish the with this we finish the presentation. Also, this type of figures you can download, copy to the clipboard, and then to paste in a given document and so on. Well, and then we finish with the presentation. Okay. We have all here in the presentation. Well, thank you for your attention.